I just want to do a couple of quick examples of polar curves before we get to kind of a bigger one. This one, find the area inside one loop. Well, I want to remind you that how we should always start this is with the formula. And remember, the formula is, I'm going to write down here, area equals 1/2 integral r squared d theta. Okay, so for us, we're going to have 1/2 integral of 4 cosine 5 theta squared. And I would urge you to graph this on your calculator and get a sense of the graph. We are going to, on the next example, talk about finding bounds by hand, but you have some options here. If you plug in 0, if you think about that, if I plug in 0 to this, theta equals 0, I get the cosine of 0, which is 1. 4 times 1 is 4. It's right here. This spot right here is where theta equals 0. And actually the graph begins tracing this way. So what you could do, if you're trying to find one loop, you could actually try and figure out when r is equal to 0. And you could, that would then shade in this area right here, and then you could just double it. That wouldn't be a bad way to do it. If you play with your calculator to just get the overall bounds, the entire shape is from 0 to pi. Pi gets you back to this original spot. So what you could do is you could say, well, 0 to pi fills in the entire thing, and then I just need to divide this answer by 5 or multiply it by 1/5. So you have quite a few options on how you want to do this. And again, I would just urge you, at least to begin with, play with a calculator to help you find the bounds. This would be a little bit maybe harder example to come up with the bounds by hand, but we could certainly do it. As I said up here, if you wanted to figure out when r was 0, we could divide by 0 and say, well, the cosine then of 5 theta is 0. Cosine is 0 at pi over 2, so you'd say, well, 5 theta is pi over 2. Divide both sides by 5, so theta is pi over 10. And you could integrate then, you'd have 1/2 the integral of 4 cosine 5 theta squared d theta, and go from 0 to pi over 10. And of course, that, like I said, it's shaded up here, would give you that blue part. You could just double this, and that would give you the answer as well. Or, to actually get one loop to fill in this whole thing, you could do from negative pi over 10 to pi over 10 of your r squared. Okay, so lots of ways to do it. Play with the calculator to get the bounds. Let's do one more example. In this one, we're going to find the area inside the inner loop. Okay, so we just want this piece right in here, like that. So one way to maybe start thinking about this is, think about the way we did our graphs the other day. We would say theta, and we'd have r, because it's not a bad idea to kind of feel out where the graph begins and ends. If I plug in 0, the sign of 0 is 0. So 2 times 0 is 0, plus 1 is 1. So when the angle is 0, r is 1. So this piece right here, this point right here, this is when theta equals 0. And then you could maybe plug in another easy one, maybe like pi over 6. The sign of pi over 6 is 1/2. 2 multiplied by 1/2 is 1, plus 1 is 2. Now, of course, it's out along that pi over 6 angle, about 2 units away, so that's probably right in here. This is probably theta equals pi over 6. Okay, so you can kind of get the sense of how this thing is moving. You say, well, it starts here at 0 and it moves up this way, and I bet it just continues moving around and continues moving around this way. And you really want to get down to when does it hit this spot right in here, because that's the spot where the inner loop begins and ends. And that spot is where r is equal to 0. So let's figure out when this function hits 0. We subtract 1, divide by 2. And we know that sine is 1/2 at pi over 6. It's also 1/2 at 5 pi over 6, so it's negative 1/2 at 7 pi over 6 and 11 pi over 6. These are the two spots where this polar curve would have a value of 0. So that means to find the area, we're going to have 1/2 integral of r squared and we're going to go from 7 pi over 6 to 11 pi over 6. And I would urge you right now to go to your TI-83 and just graph. Graph the original curve, maybe go from 0 to 2 pi so you can see the entire thing. Then maybe change your window to only go from 7 pi over 6 to 11 pi over 6 so you can see that it really is only that inner loop.